1 here for our review, and then I'm going to jump to number 14, or we'll do 1 through 4 and move on from here. Just a quick, what do I look for on these? Basically, you are looking for a parabola. If I look at number 2, I can see that number 2 has only one squared term, so that's going to be from what we've been doing, a parabola. And now if I notice 1, 3, and 4, they both have two different variables squared. Alright, so once the two different variables squared is happening, I want to see if there's a plus or a minus sign between them. So I've got a minus sign on number 1 in between my two squareds, so I don't need to worry about the coefficients, but I know there's a minus sign, so I know that's going to be a hyperbola. And then looking at number 3, I have a plus sign, but the coefficients are both 1 in front of there. The 4 or negative 4 or 4 center doesn't really matter. It's just going to make us have a circle here. So since the coefficients are the same, circle. Now if I have a plus sign in between them but coefficients are different, that's going to be an ellipse. So there's a quick review of all those types. Okay, now I'm going to jump down to number 14 and do kind of 14 through the end here, because that's where kids are having a little trouble with these. So number 14. First of all, I see it's an ellipse. Okay, when I first see it's an ellipse, I know that it doesn't matter a lot of the other information. I'm going to have this right here, and I'm actually going to have x first and y second because it doesn't matter here. So since I have a center at 0, 0, I can already do all of this information. So all I need is my a, square it, put it under here, and then b, square it and put it under there. Well, I can't tell you enough. I hope you're figuring this out, that the sketch is what can really help you here. So if I have a center at 0, 0, so here's the center for this diagram. One vertex is at 0, 4. 1, 2, 3, 4. There's a vertex. What they just told us is that the b value is 4, because that b value is the vertical distance from the center to either the vertex or the endpoint. So we square that and we put 16 in our formula. All right, and then be careful here. The length of the minor axis is 6. That means the entire distance from here to here is 6, which means the a value is just 3, because it's half of that total axis length. So that means we put a 9 in there. A distractor on a multiple choice would definitely be a 36 there, because you're taking the 6 and squaring it. But really do half of that and then square it. Okay, so then the next one is a hyperbola. Now the tricky point here is with a hyperbola, we have something minus something equal to 1. And whether the x is first or the y is first matters in the formula. So what we want to do is we want to look at the key word. And this one is a vertical hyperbola. A vertical hyperbola will have a center, and then they'll have vertices here and here. So that means it's going to look, not a great diagram sketch, but it's going to look like that. Well, what that tells me is when this is the case, that means y is going to come first in the equation. So when I go to write my equation, I know that my center's at 2, negative 4, so that's fine, but I put the x minus 2 here this time and square it, and then here is the y plus 4, quantity squared. And then we should be real pleased with the problem. Just gives us the a and the b value for the formula. So a is 3, so a 9 always goes under, the a squared always goes under the x, and then 16 here goes under the y. Okay? So this next one now is a hyperbola with a transverse axis. Transverse axis means the vertices are on that. That's all. Well, we're going through the origin, okay, through the origin, and a vertex at 9, 0. So we're going to put our center here at 0, 0, okay? And then a vertex is at 9, 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There's a vertex. Here's our center, okay? And in looking at this now, write the equation for hyperbola with the transverse axis. They really should say that the center is at the origin. I think it's lacking that information because there could be a center at multiple places actually. So this probably isn't the best question, but let's assume it says center at 0, 0 at the origin, then we would be here. But the key is, then it's going to look, I'm just doing a quick sketch, then it's going to look like that, which means the x value comes first. So we're going to have x squared over something minus y squared, because the center is at the origin, equal to 1. Well, if a vertex is at 9, 0, we just gave you the a value being 9. So right under the x squared, we square that and we put 81. And then they give you the rest of it. B is 3, so then the b squared would be 9. Okay, moving on to 17 here, an equation for an ellipse now. So if it's an ellipse, I'm just going to start by going, all right, center at 8, 0, so x minus 8 quantity squared over, and then we plus, and then y squared over equals 1. I get all of that just from ellipse and center. Endpoint at 9, 0. I'm not going to take any chances. I'm going to draw a picture here. Center at 8, 0. 1, 2, 3, 4, 5, 6, 7, 8. There's my center. And then right here at 9, 0, I have a vertex. Okay? Oh, I'm sorry. I just did that wrong. That would be an endpoint. Okay? So that's an endpoint. So what we have right in there is an a value of 1. Well, 1 squared is 1, so we can fire that into the formula. Oh, vertex is at 8, negative 10. So if I go right 8 and then down 10 all the way down here, we're going to get a gap here. Hopefully you can figure that out, of 10. So b would be a value of 10. And then when we square it, that would put 100 in our formula. Okay? So there's some more practice with those equations there. All right, moving on to the application problems here. We actually have done 18 and 19 earlier in this year. We're just revisiting these, coming back. Hopefully they're going to start making sense at some point, and the practice we do with them will make it better. We have a rectangular plot up against a river. Well, the key is that we start these problems with the two unknowns being opposite sides of a rectangle here, okay, both x. Well, here's the key, and the way I describe this to people is that if you had a 1 here and a 1 here, and you had 4,000 feet of fence, or meters, sorry, in this case, you would have 3,998 left. You'd have 4,000 minus 1 minus 1. Well, that's how we come up with this value right here. We have 4,000 total minus x, which is just minus 2x. So that represents the length of this rectangle. Well, what we're doing in this problem, and if you read it a couple of times, this will be clear, we're maximizing area. The area of any rectangle we know is base times height. Base times height, however you think about that. Length times width. So we have ourselves x times 4,000 minus 2x. And then when I distribute through, I'm actually going to get something in standard form. So 4,000x minus 2x squared. And I don't like looking at them like that. I'm going to like looking at it like this. Plus 4,000x. All right? So I want you to know the first one, or 18 here, was a little trickier than 19 because 19 flat out gave you the formula, or the equation. We had to come up with it here. But now both problems finish the same. So what I do now is I got to find the value of the vertex. So the vertex is always opposite of b over 2a. That's the x value of the vertex. So in this problem, that'd be negative 4,000 divided by opposite of b over 2a. So, sorry, I wrote that wrong. 2 times a, which would be negative 2. So the x value, when we're calculating this all out here, is going to be 1,000. So we get 1,000 here. All right? Well, that means, just putting this in a picture, there's a parabola that opens down. It's going to have a certain value here. The x value is 1,000, and then the y value here is the answer to the problem, because they want to know what is the largest area. That's the y value for the problem. So there's two ways you can do that. You can literally take the x and plug it in here and plug it in there. That'll give you the area. Or you could go back here. Then you could be like, all right, well, x is 1,000, so I can put 1,000 right there. 4,000 minus 2,000 is going to be 2,000. So I could literally plug it in there and then do the area, 2,000 times 1,000. Okay? So the answer, the area that can be maximized here, whether you plug it in here or whether you plug it in over there, is going to end up being 2 million. When you work it all out, 2 million meters squared. That's going to be the answer to this problem. Okay, now if you watch this, I'm going to do this next one faster because this one is talking about cell phones, X number of cell phones, and then minimizing cost. Well, again, it's all right there. So all we do on these is we start with the opposite of b over 2a. All right, so the opposite of b over 2a in this case will be a positive 200 divided by 2 times 5, which is 10. So we're getting 20. All right, so 20 is an answer to what? How many cell phones? So it's color coordinated here. That is the answer to the first question. But then what is the minimum marginal cost? Well, that's where you would just do C of, and we would plug in 20 here. Okay, and I'm not going to take the time on the video, but you would do 5 times 20 squared minus 200 times 20 plus 4,000. You work that all out, and you end up getting a minimal marginal cost of $2,000. Okay, that's what you would get for that problem. All right, last two now of these application problems. Hopefully, by doing a lot of these, they're starting to make more sense. Hopefully, I can draw an accurate diagram here. But understand, these can be done a few different ways. Now, I personally like to always kind of put a parabola in a diagram that looks like this, try to keep it consistent. But if I do that for this problem, just be concerned, just know that this is the water at the top now. Okay? So if I have the water at the top, this point right here is actually going to be, look at the diagram, 120 across. This right here is going to be 60, and that's going to be 60. So from the origin, that ordered pair is going to be 60 comma something. Well, that's the height, which in the picture is 25. So the first thing I got to do is get that point right there, and then know that my vertex here is 0, 0. Okay, well, the question is, and I don't know whether to bring this up first or second, but the question is, how wide is it here? Well, what's here? 10 feet from the water. Remember, the water is here. So if we're 10 feet from the water and the whole distance is 25, hopefully you can see that this vertical distance here is 15, and then the 10 will make the total 25. Well, we've been calling this x and this x, so that ordered pair there is going to be x comma 15 in green there. Okay, but I'm going back to red because the first thing we got to do is actually come up with the function's a value. So we have f of x equal to a times x minus h quantity squared plus k, and hopefully, hey, I made my k that way. Okay, but hopefully you know now that's vertex form. Okay, that's vertex form. So I plug everything in. I'm going to put the 25 for the y value. I'm going to establish this is my ordered pair. This is my vertex. So that's equal to a times my x value of 60, and then minus 0 quantity squared plus 0. So this is actually 25 equal to 3600 a. And then I divide both sides by 3600, and if I simplify that, I'm getting 1 over 144. So that is the a value for the problem. Now I'm going to switch to green, because now the whole goal is, all right, well, wait a minute, I have the a value, so therefore I have the function in vertex form with my a value, but I'm going to plug in this 15. If I put in a 15, and I know an a, I know an h, I know a k, I should be able to come up with an x. Okay, so using that idea here, I'll do that right here. I'm going to use the 15 for the y value, this time knowing the a value of 1 over 144. Still don't know the x value, but I do know that the vertex is 0, 0. Well, look at what's going to happen here. This is essentially, I mean, if you look right here, that just says x squared. So I'm going to right now multiply both sides by 144, because what's going to happen then is I'm going to have this 144 times 15, which is actually 2,160. I'm going to have that equal to x squared. Taking the square root of both sides, I'll get x coming out to approximately 46.48. And it would be plus or minus if we're just thinking math, because we could go left or we could go right with x. But understand there, take that value and multiply by 2 to answer the question. The question is, how wide is it there? So that would be a couple of those x values, or times 2. So the width is coming out to approximately 92.95 feet at the point 15 feet from our vertex, or 10 feet off of the water, which is what the question's asking. Okay, I really like this next one too, because it's very similar but a little bit different here. You actually have a lot of information right in the picture, so I'm going to try to put this on here if this makes sense. That point, according to the way we did the last one, would be over 300. It's set up really nice here. Half of 600 is 300, so over 300 of 80. So before I even talk about the answer to the problem, we know that the origin is 0, 0. I'm sorry, the vertex is 0, 0, which is the origin. So we're going to go and do exactly what we did on the last problem. We're going to go ahead and find the a value, starting with write it out again. This one, vertex form. So f of x is actually 80 equals a times 300 minus 0 quantity squared plus 0. So 80 is going to be equal to 90,000 a. Divide both sides by a, and that actually reduces to 1 over 1125. It really doesn't matter if you reduce or you leave it, whatever, you got to have your a value there. All right, well, it's a little bit different problem because they're saying how high is it here? Well, that's okay. It's just like before. We actually know the x value now. The x value of that ordered pair is 150. The y value is what we don't know. So just like the last problem, we're going to put everything into vertex form, but this time I don't know the y value. So I'm actually going to have y equal to my new a value, 1 over 1125. Okay? And then I'm going to have times x minus h. Well, I know that x is 150 minus 0 quantity squared plus 0. So I'm putting in the x this time to get the y, which is what we actually traditionally do when we have a function. All right, so now what do we have here? We got this, if you just crank out the number there. So 150 squared times this, it actually comes out to a very nice number. Work that math out, you get 20 feet. So the height there is just 20 feet. Okay, I hope this helped. I hope you keep going through the answers and keep working on them until you get them. But these applications hopefully are making more sense. All right, hopefully you are turning to be like this.